Okay, let's now take a look at a second example of Lorentz contraction in action. And in this case, we're going to look again at an example that we studied earlier, which offers us a similar kind of potential puzzle. We're going to look at this case of muons falling toward the Earth. And you may recall in this example that we mentioned earlier, we noted that time dilation plays a key role in allowing the muons to travel the distance from where they begin to where they end without disintegrating en route. And let's now give some numbers associated with that and see in detail what it means. Okay, so here is the distance that the muon travels. And as in the statement of this situation, let's assume that v is equal to 0.994 times the speed of light. And if you go ahead and calculate gamma for this, I'm not going to do that. You can easily work it out. 1 over square root of 1 minus v over c squared. That turns into 9.14. Okay, let's hold that in mind. Now let's look at a potential puzzle in this situation. We are told that muons only live for 2.2 times 10 to the minus 6 seconds. And yet, if we look at the distance that the muon travels in this particular example, let's give this a number, an experimentally verified number, 5.9 kilometers. The question is, what does that mean for the speed of the muon? Because again, if it travels 5.9 kilometers in a time from its perspective, which is 2.2 times 10 to the minus 6 seconds, then from that you can get a velocity of the muon with respect to the Earth just by doing distance divided by time. And if you do 5.9 kilometers divided by 2.2 times 10 to the minus 6 seconds, the result you get is quite large. In fact, if you work it out, as I have worked it out for you here, it comes in at more than 9 times the speed of light. So what in the world is going on? Well, it's obvious what's going on. We've done the wrong calculation here, right? Because when we're talking about things from the muon's perspective, this distance is length contracted. It is Lorentz contracted, right? So rather than going 5.9 kilometers, the distance from the muon's perspective is equal to 5.9 kilometers divided by gamma. It's shortened, and that distance is 0.65 kilometers. And now, if we use that length in calculating the speed, 0.65 kilometers divided by 2.2 times 10 to the minus 6 seconds. Lo and behold, as it must, this gives us 0.994 times the speed of light. Again, properly speaking, from the muon's perspective, it is the Earth that is rushing toward it at this speed. But the key fact that I want to emphasize here is, again, from the perspective of the muon itself, it is only traversing 0.65 kilometers. It is not traversing the length that we would ascribe to it of 5.9 kilometers. And that's how its speed works out to be the correct value, a value that is less than the speed of light.